Welcome, everybody. I hope you enjoyed the first talks already. We are today talking about the BMW car creator for creating a chaseable opponent in UEFN. My name is Andreas Brock. I'm technical account manager here at Epic Games. And together with me on the stage is Marvin Stecher. He's senior developer at our service partner, AlphaFlare. Yeah, then I think we should give you a small glimpse of what this is about.
One for the money, two for the show, three, get ready, four, three, two, let's go, 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 go. On your mark, get ready, set, go, 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 go. Run that, jump that, get up and go, 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 go. On your mark, you ready, yeah, go.
Nice. So, who in the audience already tried out that UEFN island? Did you like it? Okay. So we post the island code at the very end again, so everybody can make a screenshot or photo and try it out afterwards. So it all started last year during GDC when we dropped the UEFN beta in March 23. 2 weeks after that, BMW came to us and asked if we could develop a Fortnite map, including a new BMW car that should be configurable. And we said, yeah, of course, that would be really great. But BMW wanted to put a really realistic looking car into that environment. And we said, well, we just have 400 megabytes, but it's quite a task, but we should be able to do that. They said, nice, good. But we would also like to do a race with that car. Is that also possible? And we said, yes, of course, you can do a race. Then we needed a racetrack, and it shouldn't have the typical Fortnite cartoon look. It should be really realistic. And then we started to think about, oh, it's getting more and more difficult now. And we were still full of hope that we would make it. We created some moods that pleased the client, and so we started the project. We had almost 4 months to realize the whole project. But with every meeting, the wishes and our own ideas grew. And by the end, there was another character that should also fit into this 400 megabytes, together with a story, a racetrack, a soundtrack, a new dialogue system, and we were no longer 100% sure that we could do it. But in the end, it was working out quite good. And in this talk, we are talking about the strategies and the technologies we used to strip down the data and make it playable in these 400 megabytes. And Marvin will really do a deep dive on the technical side on the chaseable opponent. So it will get really nerdy with codes and snippets of blueprints and so on. So stay tuned for that part. But first things first, when we talk about a UEFN experience or general experience, you always have 3 key limitations. You have the performance, you have the memory limitation. In this case, it was the 100,000 units in UEFN, and of course the project size, which was a cooked project size of 400 megabytes. And we use this, I call it the magic triangle because I'm project manager by heart. So we use this and explain the customer, okay, if you pull on one side of the triangle, you have to back up on another side. So having this in kind of harmony is quite a task. And it all starts with data. Anybody here in the room that has already dealt with CAD data from automotives? Quite a few, so I can keep that slide short. So what you usually get as enterprise data is CAD data. It means it's heavy. It's construction based. You have a high poly count. You have a lot of objects in there. You have a deep hierarchy that is construction based. You have many draw calls. They come usually with scan textures, and on some OEMs, they also have their own teams inside the OEM to prepare the data, build up a virtual twin with scanned materials, and send it out for picture production, configurators, and so on. But in the end, long story short, this is far from optimal to create a UEFN experience. So how did we get the data stripped down without losing too much visual quality? First of all, you delete everything you don't see in the game. That's maybe the easy task. Then it got more and more complicated. We used the modeling tools. We also used the reduce polygons function. This gave you a really great opportunity to reduce poly-based while preserving certain aspects of the geometry. So you wanted to keep the borders, you wanted to keep the UV borders, but also the shape borders and stuff like that. And Nanite could resolve all of that, but then it's not working on all of the platforms we are trying to support. So we had to strip it down in any case. This is, for example, a screenshot of the simplify options we have used. So there are a couple of different simplifier types in there, but in the end, we used the UE standard one, and we reduced the amount of polygons from 100 to 10 to 12%. And as you can see later on, it really looks stunning. We also used cleaning geometry, so on a patch-based geometry cleaning, we replaced or simplified geometry with textures, but we need to be careful to not blow up the memory footprint by using huge textures instead of geometry, so there needs to be a trade-off. And in the end, we were able to reduce the polygon from 7.5 millions to 160K triangles. And we are not tricking you here. These are really different cars. And as you can see, you barely see a difference, at least not in the actual game. Another strategy was to combine textures to ORM pack textures. So you combine AO, roughness, and so on in one single texture. Texture resolution is also an important topic. For example, you play it on maximum full HD or maybe 2K, and then you think about, okay, how big do I need the texture to be to really get a good visual representation in the game? There is no need to have 4K or 8K textures in there because you simply won't see it. It gets mapped down anyway. We also used a certain strategy to combine certain textures. I will show that later on, and of course, look out for HDR cube maps and use the least amount of unique textures you can get. Talking about the memory limitations, I said we have just a couple of 100,000 units for the car itself, but there's also the environment and the racetrack, and there are a lot of props in there. We have tires, we have bottles, and battery packs, and so on. So there needs to be a lot of optimization being done to really strip it down and get it into the memory limitations. So I talked about reusing textures. What we did is we created one texture, which you can see here with the different colors on the texture, and then we used the UV space to actually assign one color to parts of the car. So for example, you were able to combine a lot, which helps in terms of draw calls. And you were also able to assign this material to 50-60% of the car, because you can just change the color by using a different UV space. And this gives you a lot of freedom later on for other parts you were focusing on. So, for example, we used it for all the icons. We used it for plastic parts in the exterior and the interior. So there was a huge part of the car that was just combined together. You need to be careful with combining because you need to rig and animate stuff, but this strategy helps quite a lot. Also, in terms of an environment, I said we have a lot of tires, battery packs, and so on in there. What we did, we used hierarchically instant static meshes. And this allows you to render a large number of static mesh instances, while optimizing performance by grouping similar instances together and rendering them as a single batch. Even if they are merged into a single batch, hierarchically instant static meshes still allows instances based on the camera distance. So LODs will still work depending on the distance of the player. We did a Python script, and the good thing is, and Marvin will tell you as well, that you can copy and paste stuff out into Unreal, do modifications, and copy and paste it back. And that's what we did here. We had a Python script that was basically running in Unreal, batch replaced all the assets with instant static meshes and put it back into the scene. And this way, we were able to reduce our memory footprint quite significantly from 150,000 units to 100,000 units, just for one batch of objects. So this was quite a huge impact on the memory limitations. Also, the performance. I talked about Nanite. Nanite will help you on high-end gaming consoles on the PC, but it won't help you on last-gen consoles, on mobile handhelds, and so on. So you need to use geometry LODs. What we found out as a sweet spot was using 3 LODs, because if you use more, then you get a larger memory footprint, and again, it's costing you on the other side. So you're pulling one side of the triangle and decreasing the height of the triangle on the other side. So it needs to be all in balance. And what we also did, we defined LODs per engine scalability level. So that means, for example, on a handheld PC, we start right away with LOD 1. On the next gen or PC, we start with LOD 0. And on an even more or older hardware, we can directly jump to LOD 2. So we defined it per platform, more or less. Also, when we started, we had quite a huge draw call. So there was a lot of construction history in there. There was a really deep scene tree. And in the end, we were able to bring this down to, I think, a couple of hundred, 300, 400 draw calls. So this is giving you a lot in terms of performance, but also memory-wise. And the same material technique I showed earlier is helping you even further here. And that's a typical screenshot what you combine if you just look at the car paint parts, because the bonnet is not moving, but the trunk is moving, the doors are moving, and the bumper has some other aspects we need to consider, but we can show that later on. And in the end, the topic visual fidelity. It needs to look good. You have to test it on each and every platform. That's a very important aspect. And you have to do that throughout your whole development cycle. Don't do it at the very end. Do playtests in the middle, during developer iterations, and so on. What we also used is that we turned off shadow casting quite a lot. We used it on very specific areas. You have to keep your light radius rather small, and you should avoid overlaps because this is doubling your computing time. And we just use stationary lights, so no dynamic lights. I think in the end we ended up with 2 or 3 lights that really casted shadows. The other lights were not casting shadows. We did that just by faking shadows via texture. And in the end, the first part of the project, which is the configurator, was done. We had a configurator that was similar to the ones you can find on each and every homepage of an automotive builder. The user is able to configure the new iX2 with a lot of real options like car paint, colors, like interior trims, be it leather or fabric seats and so on. And you can do it together in a group, watch at it, open trunk, open the doors, walk around, and of course we built in some Easter eggs like the Der Burger as wheels, funky glowing wheels and stuff like that. And you could also place pumpkins and other widgets in the trunk to show the volume of the trunk. So we had Christmas decoration also in there, which was quite funny. So yeah, you need to check it out on your own. And with that, you're more or less done with the configurator part. And then the second part happens, which is then the part Marvin is presenting, because then the real chase is starting.
Thank you, Andreas, and good morning, everyone. Yeah, so welcome to the second part of our presentation, where we'll tell you about our computer opponent and how it was developed. So after the players finish configuring their dream car, unforeseen things are happening, and a thief will steal the freshly configured car. And of course, our players want it back and will be provided racing cars to pursue the thief. But yeah, the thief is an experienced driver and will also drop traps onto the track and will hinder the players from catching her. So our task was to build a computer-driven car opponent on a predefined track. And as we know, we will have a predefined track which the opponent must be able to navigate it to flee from the players. And to make the chase interesting and challenging, the thief also has to react to our players when coming dangerously close, and some escape maneuvers must be done. But this is a game and should be fun. We must, of course, accommodate to our players, and so it should be possible to catch the thief at one point, and also by a variety of differently skilled players. Okay, now shortly about the team at AlphaFlare. So the project team consisted of experienced Unreal Engine developers and artists, but we did not come in any contact yet with Fortnite Creative or at that time the just recently released Unreal Engine for Fortnite and its new programming language Verse. But of course, we had assumptions of what Unreal Engine for Fortnite, or short UEFN, will be. And we thought this will probably just be Unreal Engine with some additional Fortnite features, and Verse will probably be something like blueprints as code. Well, everyone who has worked with UEFN yet will know how naive we were, because from the outside it looks a lot like Unreal, but pretty much all the advanced functionalities are gone. So as a result of this, we could not use any of the AI features Unreal normally has, which would include behaviors or even navigation meshes. And also, although Verse looks very promising for the future of Unreal in general, it currently lacks a lot of functionality in comparison to, for example, Blueprint or even C++. Yeah, but our computer opponent needs to move, and this is what the first chapter was about, and it's called Making a Move. So without any AI functionalities, we realized that we have to find an alternative, and after some brainstorming, we concluded that the best bet would be to use predefined animations. Therefore, let's take a look at what UEFN is offering us. So first, there's the animation controller. This is a class that every prop in Fortnite inherits, and developers can utilize it to animate the mesh which the prop represents. And the animation keyframes are provided as an array in the data format of called keyframe delta, which is a custom data structure, and where we can define location, rotation, scale, the play time of the keyframe, and the desired interpolation method of each frame. By this being a verse class, the animation controller would give us a good control via code, but is lacking an option to vary the playback speed. So it would be necessary for us to vary the playback speed because we have to, at some points, vary the speed of the opponent, and when this is lacking, it's kind of hard to change the speed. Also, it would be necessary to create the whole animation in a code array, and as you can imagine, this would be horror to manage and certainly no easy or fun task. Furthermore, we had issues with the lacking option to define the interpolation methods for rotation and translation individually, and there's no keep state functionality in this, which could cause a lot of issues when using multiple animations, because when you stop one animation, it could be that this part that was animated of the car or the whole car would just reset to the place where you started this animation. Therefore, we deemed the animation controller not as the right tool for us. The next one is the cinematic sequence device. And just for reference, if anyone, because not everyone will probably have worked with UEFN, devices are actors that can be added to your level and provide some certain functionality. And in this case, the cinematic sequence device is a device which you can use to play a level sequence. And being able to play level sequences would allow us to use the level sequencer, and the level sequencer would be the tool we would like to use to create a car animation. And yeah, so this would be a preferred way to play the animation and create the animation. Also, the cinematic sequence device exposes a variety of functions to verse, which would allow us to build extensive logic around us to manage things like when it's starting to drive, the speed, and so on. Furthermore, level sequences have this keep state functionality, and it would enable us to play animations without having to worry about any meshes resetting their position after an animation has ended. But the cinematic sequence device is, or was, lacking a playback speed setting that we needed to change the driving speed of the car. So in some of the updates that came later on, this option was added to the cinematic sequence device, but at the time when we implemented the opponent, it was no option. So we looked further, and what we found also was the control rig. And this is a feature which shipped with Unreal Engine 5, and allows developers to programmatically control a skeletal rig. And luckily, this is also a feature of UEFN. And with the help of the control rig, we could animate the car movement itself, but also control smaller parts like the wheels or the trunk and so on. But there isn't a functionality to create any animation with it or to import existing data, except for one small node, which is called curve. And this node allows to define floats on a XY coordinate system. So in theory, we could define 3 of those nodes for the translation, so X, Y, Z, and another 3 nodes for the rotation, roll, pitch, yaw. But telling someone to create a car animation by defining values in 6 different curve nodes would probably be a cruel task and does not promise any good results. So, but as this was still looking like the best option because it has so much, it's such a mighty tool, the control rig, and it's just lacking a proper tool to create the animation. We brainstormed and thought, so is there maybe a way to import the level sequence, because we want to actually use the level sequencer to create the animation. So is there a way to import a level sequence into the control rig as 6 different curve nodes? And yeah, spoiler, there is. We found a solution. So if you're familiar with Unreal Engine, you might know that basically every data you can copy paste in the editor can also be pasted into a text file, and it's kind of human readable and exposes the data of the structure you just copied. And in this case, we copied the track level sequence where we just defined 2 keyframes to move a car from A to B. So just a simple animation for testing. And in this purple box, you can see that we can see our defined keyframes in there with all its values like location, rotation, scale, and the time of the keyframes. So we did the same thing for the curve node, which is the node from the control rig, and we found our defined values in there too, just formatted a little bit different than in the level sequence data. And yeah, here you can see this is just the x-coordinate translation track of a level sequence and the curve node containing the same values. And the values you can see, let me point you here, for example, of key 2. So this is the sequencer data. You can see the value here, and this is the curve data, and you can see the value here. So no difference in values, but the thing that differs is the time. So the time value of a level sequence is the key. So every key has a frame number that is the point where the animation you defined there should be happening. And for some reason, you can see here, the value here is 48,000. So in this copied data, everything is multiplied by 1,000. I don't know why that is, but it is the case. So it's just 48,000 is the frame 48. Yeah, and in the curve data, you can see the time varies from 0. It's not standing here. If it's 0, the time is just not put into this data here. So here's you have to imagine it's standing time equals 0 here, and here's time equals 1. So it's going from 0 to 1. And this is actually something that was chosen by us because we wanted to interpolate the animation just from 0 to 1. So 0 would be the beginning, 1 would be the end of the animation. So to convert our level sequence data to be used in our curve data, we therefore have to normalize the frame number to range from 0 to 1. Yeah, and to do this, we divide the keyframe time by the tick resolution, which is given in the copied data in the end here. Tick resolution equals 24,000, so 24. So each tick is 24 frames. And if we take the keyframe number from key 2 and divide it by the tick resolution of 24, we find that key 48 has the playtime of 2 seconds. And to normalize the playtime, we just have to divide the playback time by of a frame by the overall playtime of a level sequence, because the example level sequence consists only of 2 keys, and the last key is the key 2. We know that the whole playtime of the sequence is also 2 seconds, so 2 seconds divided by 2 seconds is just 1.0, and 1.0 is the final frame of in our curve node. So after adding the converted keyframes into our curve node data, we can copy the node back into our control rig. So essentially, we can just, we could manually take all the level sequence data, format it in the correct time with the time values we need for the curve node, copy it back in the copied curve node data, and we could paste it back into the control rig and would have this animation in there. But this would be a time-consuming task, so we automated this. The workflow would be we copy-paste the level sequence data into a text file. A Python script would read this file, save this, would convert this to curve nodes, 6 curve nodes, and then export it as 6 different files, which we could copy back into our control rig. And this is an yeah, here you can see the setup of our control rig for the rotation part of the animation. So on the left, you can see our 3 curve nodes representing roll, pitch, and yaw, and every curve node has connected a node called evaluate curve, and the evaluate curve node allows us to retrieve a value from a curve node at a certain point of time. And yeah, the retrieved values get combined into a quaternion, and this gets applied to the control component of the root bone, which controls the car's rotation. And the translation just gets applied in a similar fashion. By setting the progress variable in our control rig, we can control the playback time, or the playback of the car's animation, so from 0 to 1. And now it gets tricky again. In Unreal Engine, you would just expose this progress variable, so it can be controlled by a managing blueprint. But in UEFN, we don't have blueprints, and VERSE has no functionality to access the control rig. So the control rig seems like a locked fortress with no way of communication with the outside world. But every story needs a hero. And this is where I will be presenting you the magic cube. So the control rig has one functionality that can be used to retrieve information of the surrounding world, and that is the sphere trace function. And our idea to control the animation progress is based on the concept of essentially every media player, where the user can drag an object on the timeline to control the playback progress. And in essence, that is the same construct we built with our magic cube. So the timeline is an upwards facing sphere trace, and the progress slider is the magic cube. So to play our animation, we are moving the magic cube upwards, and the control rig measures the distance between the current and initial position of the cube, and the sphere trace is 100 Unreal units long. So when the cube has traveled, for example, 50 units up, our playback progress would be at 0.5, so half of the whole animation. Yeah, here you can see the implementation of the progress calculation. So we have a sphere trace, so you can see it here, which traces from the initial cube location, which is defined in here, minus its half length, because we want to trace the bottom of the cube to the maximum travel distance, which is 100 units upward of the initial location, which is done here. And if the trace hits the cube, we calculate the distance of the collision location to the trace start location and divide this by the maximum travel distance of the cube. And this calculated value is the new progress value for our animation. Here I have a short example video where I'm where I will manually drag the cube in the editor. So on the left side, this is our magic cube. On the right side, this is the car. And now I'm dragging the cube upwards, and you can see our car is driving on the track. So the cube is essentially controlling the car's animation. You can see I will put it backwards again, and now the car is driving backwards. So essentially, it's like a media player scroll function. So we almost finished what we tried to accomplish. We are able to create an animation by using the level sequencer and convert the animation so that it can be used by the control rig. By moving the magic cube, we can control the playback progress and also the speed of the computer opponent's driving animation. But one thing is left. How do we move the cube? If you remember, in the beginning of the presentation, I talked about the different animation functionalities of UEFN and why we have decided to use the control rig. But now we are again at the point where we have to think about how to animate a mesh in our level. So yes, it is kind of a full circle moment, but we have trivialized the problem a lot. Instead of having to find a method of how to animate a car on the racetrack, we only need to animate a simple cube going 100 Unreal units upwards. And yeah, to animate the magic cube, we use level sequences via the cinematic sequence device. And what you are seeing in this screenshot, and these screenshots are multiple level sequences that move the magic cube upwards with different speeds. So because the cinematic sequence device had no playback speed option at that time, we were forced to create different level sequences for each speed. And the main speed sequences are marked in pink and serve as the main sequence to drive at a certain speed. And the purple marked sequences are transition sequences, which are used to accelerate or de-accelerate between the main speed sequences. So for example, in the top screenshot, you can see a sequence called B main normal, which is just the normal speed. So main stands for main speed sequence. And if the computer opponent wants to slow down, the next speed setting would be half speed. So to reach half speed, it would first play the sequence trans down to normal to half, to deaccelerate down to half speed, and afterwards it would play the sequence A main half to stay at the speed. On the bottom screenshot, you can see our booster sequences. We have booster stripes, you can see here, all placed all over the racetrack. And it will boost the player, but also the AI opponent. So for every main speed sequence, there must also be a boosted sequence, as well as 2 transition sequences for accelerating and deaccelerating to the boost speed and back to the main speed we are coming from. And because this was a huge factor for balancing the difficulty of the race, we created also a Python script that automatically generates these sequences for us, and that we can use to quickly iterate over different speed settings. So the control rig also enabled us to dynamically calculate the animation of the wheels based on the motion of the device. And to calculate the steering angle, we calculate just the local jaw angle between the forward vectors of the last frame and of the current frame. And by additionally calculating the determinant, we know if we're steering left or right and apply a positive or negative steering rotation. And the turning angle is based on the distance that the car has traveled between the last and current frame. And this traveled distance gets divided by the circumference of the car's wheels and multiplied by 360 degrees. And yeah, when both steering and turning rotations are calculated, we apply the steering rotation to the turning rotation. And this is the final rotation of the wheel rotation for this frame. And you can see here how it looks. It's not a perfect solution you would find in any serious race game, but it was sufficient enough that it looked good for this opponent, and that did not took any big work for us. So this concludes the implementation of the base framework to animate our computer opponent. The next chapter will be about the creation of the actual driving animation of the car. So creating a smooth and believable car animation by hand is a time-consuming task, and by the time we finished the groundworks for the computer opponent, the racetrack was still being worked on. It was undergoing constant changes. And if we would create a driving animation now, it would be certain that the animation would have to be changed many times to accommodate to new map changes. We had to prevent a situation where we either had to wait a long time for an updated animation because someone has to manually change it, or to refrain even from map changes because a new animation would have to be made. And this is when we started to think how we could automate or improve this process, and so that it takes the least manual labor to create a new driving animation. And when you think about car commercials, the car you're seeing on the screen is mostly CGI, but the motion of the car is often based on a real car that was filmed. So we thought, can we do kind of the same? We created a new project in Unreal Engine 5 and imported the car model of the computer opponent and a simplified version of the track. Based on the car model of the computer component, we created a player drivable car, which we could now drive around the track. So let me show you. You can see here, so this is the process of recording an animation. So you would create a level sequence, a new one for this recording, and just set the recording time to just a long time, and then you would just hit play, add our pawn, which is the new car, to the recording, and press record. And then we just have to drive around the track. And the red lines you're seeing indicate the area where we should be driving between. And you will see there are some blue boxes, and this is the position of our booster stripes on the track, because the AI can also use this booster stripes. We have to know where they are located. And you can also see we kind of are going at 50 kilometers per hour, so we put in a speed limiter in there to have a kind of constant speed, because we want to vary the speed in UEFN, and it should be at a constant speed in the animation. So for demonstration purposes, I'm stopping the recording now and will open the recording. And in here, we remove just everything we don't need, which is everything besides the transform track. And after cleanup, we can just copy the sequence track into a text file, process it with the formerly mentioned Python script, and insert the generated curve nodes into our control rig. And yeah, by using this dedicated record project, we could create a new animation in around 20 to 30 minutes. So, chapter 3, escaping the players. This is the last chapter, which is how the computer opponent reacts to players and how this serves to create an engaging and fair experience. So, as mentioned in the beginning of the game is about, of the presentation, the game is about catching the thief to reclaim our dream car. The players can catch the thief by getting close to the car and stay there for a few seconds to hack the car and shut it down. For the chase, we had some guidelines. We want the chase to be engaging, so we needed to assure that catching the thief isn't too easy for experienced players, but also still achievable for the less skilled audience. We also want players to feel that catching the thief was a team effort, and we felt it was crucial that players stick together to achieve this. We don't want players to miss out on all the action because they can't keep up with the others. And the players should also feel like it's always possible to catch the thief. So if the thief manages to distance herself from the players too much, there must be always a possibility for the players to catch back up to her. In the first chapter, we presented that the computer opponent has 3 different main speeds, and we utilize these speeds, get settings to either wait for players or to flee when they are getting dangerously close. So we define certain distance thresholds for each speed setting to ensure that the thief slows down when the players are too far behind and to accelerate again when they are getting closer. The thresholds you are seeing here are designed so that it should be impossible to catch the thief in the beginning of the game. And as the time goes on, we scale the speed thresholds down, which allows players to get closer before the thief starts to accelerate. Additionally, to the distance threshold getting longer, we also implemented a progressive slowdown in the recording itself, so by lowering the top speed in the recording project over time. So it's also built in the recording itself. In this video, you will now see the described mechanics in action. So in the upper left corner, you can see the player perspective. The big picture is showing the rear view of the computer component, and with additional information in the lower right corner about the current speed and the currently used speed sequence and the distance to the player. In a moment, you will see that the player will collide, you can see it here, with a trap dropped by the thief, which will slow down the player drastically, and therefore the distance between the player and the thief will increase fast. So the video will resume shortly. And you can now see that the distance is going bigger and the computer opponent is slowing down. Now it's on normal. Now it goes from normal to half, and it's now at half. And you can see now we are driving at around 50 kilometers per hour, but the player is coming back fast. So we are accelerating again, half to normal, normal, even to impossible, because the player is now really close at 15 meters. And you can see there it's flashing shortly. This is even a catching attempt, but the computer opponent is able to evade that. But to achieve our guidelines, we had to implement additional mechanics. So if only the AI slows down to wait for players, there's still a chance that players will fall behind and lose a connection to the player field. That's why we've also implemented a boost mechanic that periodically boosts players who are too far behind from the rest of the player field. So different speeds for the computer opponents and boosts for players who were left behind worked really well, but made the race very predictable, as the thief was called almost every session and at roughly the same time in our playtest. So we gave the thief also some countermeasures that she would randomly throw on the track to hinder players, and especially when they are in range to catch her. This made the game a lot less predictable and also gave the thief a bit more character, because it was not just a driving car on the track, but also it did something. So, summary, as we approach the end of our presentation, let's briefly recap how we approached the task of implementing the computer-controlled opponent in our experience. So we recorded the car's animation by using the level sequencer in a dedicated project with Unreal Engine 5. By creating helper Python scripts, we converted the recorded level sequence data to 6 curve nodes usable in the control rig. These 6 curve nodes are driving the animation in our control rig, and by utilizing the sphere trace functionality of the control rig, we can control the animation progress by moving a cube in the level. And to play and control the animation, we are using level sequences that move the cube upwards at different speeds. So a short slide about what has changed in the meantime. This project was done in at the very early release phase of UEFN, and obviously much has changed in the past year. And so the cinematic sequence device now features the playback speed setting. So in essence, we wouldn't need the construct of Magic Cube and control rig anymore. You could have the car's animation in a level sequence and vary the speed of the car by just altering the playback speed. And if you don't want to have a predefined animation, the recently introduced custom NPCs could also be utilized to build a pathfinding system to navigate around the track, because they have a simple pathfinding function. And also the just released scene graph opens up new opportunities by being able to retrieve more information about the world around the car. So much more options now to actually implement a pathfinding system, and so that you don't have to rely on a predefined animation. All right, this concludes our presentation, and I would like to welcome Andreas back on stage.
Maybe one last thing. We have the Auto Summit tomorrow, so if you're an attendee of the Auto Summit, you can meet us there, ask a lot of questions. It's more an open format. There is lots of time for discussion, so yeah, see you there.
Thank you so much.
Thanks.